Hello, everyone. My name is Husseini, and I'm going to talk about logistic regression today. Um, this is one of the techniques used for a classification, and don't let this term actually fool you. Um, I'm going to talk about a little bit about math behind this method, and then we have an example that we're going to use breast cancer data set using Python and one of the libraries which is very popular to use machine learning model like logistic regression would be scikit-learn. That's what we're going to use. All right, so let's start with this model and look into the math behind this model. All right, so logistic regression, you're going to actually use a few things about this. You're going to use sigmoid function for classification. In this case, we're going to talk about binary classification. So it means that you have only two classes. So either would be example like a spam or not a spam problem. So in this case of breast cancer, if person has cancer which is malignant or benign, whatever you have two classes, or like you apply for a loan, either you get approved or denied. So that would be these sort of problems. All right. So the way that this one works, based on sigmoid function, so if this is a sigmoid function, it is worked like this. So this is X, and this would be Y, for instance, this plot. So it is like S shape, supposed to be S. And this 0, this is 0.5. Then X going to go to positive infinite. This one goes close to 1, and an X going to negative infinite number, and this is going towards 0. The reason actually using this sigmoid function and the equation for sigmoid function, it's like this. We have an X. The equation would be 1 plus e to the power of minus x, which this one is exponential number. Okay, so the reason they're actually using this sigmoid function, because the range for this function is between 0 to 1, and that's what actually works fine for us when we are dealing with probability. That's a reason they're using that. Okay, so how do we actually use that for binary classification? So we have two classes in here. So basically, our target belong to class 0 and 1. So in case of breast cancer, maybe 0 is benign, and 1 means malignant. Okay, so how do we create this one? And this is the reason actually it is, they call it regression, because it actually it is actually using linear regression model to do that. So if I use the term z, for sigmoid in here, our function z would be like this. Z is, it look like theta 0, I equal to 1 to m. This is theta I and xi. So these are actually, and this is look like linear regression. Linear regression equation. You should see that this is linear. So that's what the term regression coming from. In order to actually use this model, these are actually unknown. These theta, starting from theta 0, theta 1, theta 2, theta m, these are unknown. And the goal is to calculate these ones. And when you see that in X in here, these are the value from our features. So whatever that our model depends on. So if you have spreadsheet, basically when you use that, you have a spreadsheet. This Y would be target. And you have a bunch of features in here. You're supposed to be a straight line. Bunch of features in here. Any of these ones, they are actually known, and you have the targets. In this case of breast cancer, so the target would be 0, 1. So these are all known. And we're going to use this information to basically train to a model, and train on model to calculate those theta to find out. So all the knowledge actually would be create these data based on our data sets in here. Okay, so logistic regression, which we are using sigmoid function, basically gives us the probability. And in this case, we have two classes. It's either class 0 or 1, which is a binary. We're talking about the binary classification, but for other multi-classes, so you have, so for instance, if you wanted to classify news article in different categories, you might have more than two classes, which is not binary. So for instance, news belong to sports, politics, health, and so on. So that would be multi-class. And the idea is basically the same thing, but we're going to talk about binary. So the equation that we're going to use that in here to find these theta would be like this. So we're working with probability. You have the X. And you might see that these is writing in bold. So it means that they are vectors or matrix. And this would be equal to our sigma C, which we know that that's the equation look like. And Z is what we have actually written above, and that would be something like this. Okay, so what does this equation tells us? So based on, so any one row of your data set, if data set is belong to malignant, that we wanted to we'll see that what's the probability would we want. So if this case is this row is this information, the person has cancer, for instance. So we want it to be that probability would be one, that would be highest. So this probability we want it to be one because that means that we predicted correctly. And in this case, this probability we want it to be zero because the person doesn't have a cancer, it's benign. And so we wanted to have this one to the highest probability. And we know that the probability is the target is one. So we probability we want it to be highest. Highest, or in this case, would be and the same thing, so this probability based on this features, the probability is zero, means that we are, that probability is one in case of this value is zero. So we are confident that we predicted correctly. So how do they write for these two cases? So we have, for this sample, for instance, we wanted to make sure that our model predicted correctly and target is one. And in this case, we wanted to be sure 100% that's the ideal, 100% that this target is zero. So in order to do that, so we have two classes in here. So one class that we wanted to target would be one, and another class or under sample, for instance, we wanted to the highest probability as a target for the benign case would be zero. And so we only have two classes, two probability or two outcome. So based on log probability, whatever this value is, if this probability, for instance, 60%, probability being benign would be 1 minus 60% or 40%. So this equation would be 1 minus sigma, because we only have two outcomes. Okay, so we have assumption in here that all the samples that we have, all samples are independent. So when samples are independent, so we have the rule of P, A, and B, for instance, when they are A and B and independent is equal to PA times PB. So imagine these are two samples or two rows from your data set. So the idea works. So based on number of samples that you have in here, so that's the same things happens in here. For our example, based on this independent equation that you see that in here would be something like this. I'm going to talk about what's going on in here. So again, these are all would be, so these are not just a number. These are either vector or matrices, and you see that they are actually written in bold. And I have a lot of options in here. And this would be like this. X, Y, I'm going to talk about this quickly. Theta, sigmoid, theta, Y. So this is theta, X, and this is 1 minus 1. So the idea coming from in here, same idea. And these are basically number of samples that you have based on number of samples. But you see that y, these are, this is basically give you the probability. So this is x, probability of y given x, and that would be for every sample. So if your sample for breast cancer, for instance, the sample the target would be molecular 1, so that would be based on that row, or another sample, the target is 0, or person doesn't have a cancer or benign. In that case, the probability of finding when y is 0. So this is a case. This part is a case that y is 1, and this is where the case is y is 0. So that's where you calculate that. So that's the probability for the case of y is 0, and that's the probability for the case of y is 1. So to give you the probability. So again, these are multiple samples. We assume that the samples are independent. So based on this equation, we can basically multiply them. So and we actually, this would be, we can write that as a likelihood to see that if you have multiple samples. So the likelihood, see that theta, because that's subjective, we wanted to calculate that. For every sample, so imagine we have n sample. And this is the multiplication, not pi, that's a multiplication. So that would be y, to yi sample, given x based on the sample of that feature, which would be equal to this way. Again, this is not pi, it's just the multiplication. This is yn, so we calculate for each sample would be x for that sample, yi multiply by 1 minus sigmoid x I for that sample to the power of 1 minus I. Again, this is the probability. In that case, our target is 1, and in this case, the target is 0. So that 1 minus 0 is the case of probability and target is 0. And this is the probability for the case of which is target is 1. So this would be 1, and also 1 minus 0. This would be 1 also, and for those samples. Again, so when we write something like this in here, this is based on that input, our target is 0. But this is the probability. We wanted the highest probability. So in this case, we want this one, the highest would be probability is 1. And so in that case, if that probability for this sample, so for instance, the person doesn't have cancer, if we wanted to, this probability would be 1, doesn't have a cancer, this is a benign case. So if this probability 1, and we only have 2 outcomes, so this probability for that sample, this would be 0, because we have only 2 outcomes. So basically they are opposite of each other. So we wanted to have the maximum value for each case. So for each case, probability would be 1. So we wanted to maximize that for all the samples. We wanted to maximize this. What you can see that here, these are probability. You can have a lot of samples. So this is, it could be small values. Could be a small value. So what they do that, they actually take the logarithm. They take the logarithm of this equation. What actually logarithm helps us we can take the derivative, and so that derivative would be linear. That would be very easy to solve. So that's what they do that. So this equation, so might see that as LL theta, which is taking derivative of this equation. If you take a derivative of this equation, this multiplication would be converted to summation, and after that we can take a derivative respect to this theta to calculate that. That would be very easy to do that. So if you do that, this for each case, this will be converted to summation for each case, and this is what we have that for each sample. So this would be converted to summation. So if you have n samples, so for instance, you have 10,000 rows, so this n would be number of rows, which would be 10,000, and this is if you take the logarithm, the equation for each sample would be like this. You take the logarithm of this, so that would be logarithm of this. For that sample, for the first term, and we will have, this is going to in here, multiply by logarithm of 1 minus sigmoid theta. Sorry, let me keep writing this. X, I. So we will like this. And we wanted to maximize this. This would be maximized. So each one, if that probability correct for example, so this would be maximized, and it means that each probability would be 1. So the goal is to maximize this. So all the information that we want would be available in these theta. So that's our objective, to calculate these vector of theta. So that's the objective, to find that, to maximize this likelihood and log likelihood. And again, the reason they're doing that because it would be a lot easier to take a derivative of that. So we're going to use that to gradient descent to take the derivative. The outcome would be linear. Very easy to do that. So in order to calculate, to find the optimized theta, what they're going to do that is they're going to use gradient descent. So if you have a function like this, so imagine this 2-dimension that we have in here, and the value has one value, and this is f theta. If I wanted to find a value that maximizes this, which imagine this is this point. So you can start at any initial point, you take the derivative until you find this value. So this is basically gradient descent. So that's what you can do that. They take the derivative respect to that theta, that would be equal to 0, and this theta, whatever this value is, theta max, optimal value would be calculate that. So this is actually, this is exactly what is happening in here, and take the derivative, and that value give us the maximum likelihood. Okay, so how do they do that? One thing, when we have, when we're using gradient descent to calculate these theta, so we take the derivative of natural logarithm respect to any. So we have we have different values for theta. So that would be theta 1. We talk about theta 2, theta 3, and I think that we have theta m. So this is m is number of, based on number of features, not the number of samples. So basically, for a spreadsheet, it means that how many columns that you have. We take the derivative with respect to each of them. So we have that uh, uh, log likelihood, and we take the derivative with respect to any features, any of these theta, which relate to any features. So this j belong to 1, 2, and m. So that's what they do that. And so this is what basically a starting point. They take the derivative until for each theta, we get that value. So what they do that, so they keep iterating. So what we get, that equation would be like this. So this is a new value equal to theta of the old value. And that would be, we have some learning rate and multiplied by this equation, this derivative that you have on old value to theta j old value, and keep updating until we get our optimized value. This is the learning rate. So what we need that in here to calculate this. So this is, so we need to calculate this derivative. So how do we do that? So in order to do that, this is how it works. To make it easy to calculate this, we can actually use chain function, and this is how it works. So if I wanted to take the derivative of log likelihood theta for any theta that we have, to respect to theta j, I can use chain function. Sorry, chain rule. It may actually make it a lot easier for us to calculate that, this derivative. So I can do something like this. Take the derivative, respect to p. To derivative of p, respect to theta j. So I've defined p in here as my sigmoid function. Again, this is a vector. I define p as sigmoid function because of chain rule, I can do that. And we'll see that how I actually do that, what happens. And then we have another, and this is, we define as z, just theta x, z, and we define as z. So now we do that another chain function with respect to z. So that would be log likelihood theta, respect to p, and again, another chain function, which goes to respect to z, and then here to theta j. And we'll see that what happens. Okay, for any sample, I'll look into log likelihood we have in here. For any sample, or one sample here, and we add them up. So this is, I can take the derivative of one sample, and these are different, and we take the summation. So for each sample, so this log likelihood would be 1 times log actually make it simpler. So this is our p, log p, plus 1 minus 1 This is log that would define a p down there, be 1 minus p. This is for each sample that we have n sample, and we can take the derivative of each one and add them up. So that's what we can do. Okay. So I have, for each sample, log likelihood theta would be y plus p plus 1 minus 1 log 1 minus p. Okay, so now I'm going to plug it in here. And we're going to calculate that. So we can calculate this equation with respect to p. If I do that, I will get with respect to p. And in this case, I will get, this would be 1 over p. And in this case, these are constant. And this would be 1 minus p. Okay, so take a derivative of this one. So that would be minus, and this would be in here. So this is what we get. So that would be our first term. So that's a derivative. Now, we have the second term, which is p respect to z. So if we define p as sigmoid z, and we wanted to calculate, sorry, this is p respect to z, and we wanted to calculate derivative of p respect to z for the second term. And this is for a sigmoid function, and if you take the derivative for a sigmoid function, the equation would be sigmoid z times 1 minus sigmoid z. So that would be the equation for the second term. Now for the third term, so we have theta z derivative of z respect to, so this is our second term. This is our first term. So at the end, we multiply each other to each other. So the third term is derivative of z, which is respect to theta j. And we define z as this formula up there. And again, these are vectors multiply each other. Which is basically, if I write this in, would be theta 0, x0, theta 1, x1, theta 2, x2, and until we have theta. Okay, so we have theta j, xj, and it goes to theta m, xm. So if I take the derivative of the equation with respect to theta j, so basically all of them would be 0. None of them depends on theta j. And we only have this one. So this would be, gives me xj, which is my third term. And we keep multiplying all of them together. So that would be our derivative. So my derivative of the whole thing, theta j, would be the first term that we got it in here, y divided by p minus 1 minus y, 1 minus p, multiply second term, that was sigmoid z, multiply 1 minus sigmoid z, multiplied by xj. So we have three terms. So this is the third term. This is coming from the third term. This is coming from the second term. And this is coming from the first term. So we got that. This is the first term. This is the second term. And this is the third term. And we actually, when we can do that, we can simplify this. So this would be p times 1 minus p. So this is get 1 times 1 minus p minus p times 1 minus y. And sigmoid z, we define this one as p. So this is P, y minus P, xj. So these cancel each other out. You can calculate, this is what you have, xj. So you can calculate this one. So this would be 1 y minus yp minus p plus yp, py times xj. So that what this is simplified. Yeah, this is simplified. And this is what we get. We get y minus p xj. Again, this is, we are still in here. J. And I'm going to plug in. This is would be y minus p. It's still theta x. This multiplied by x. Okay, so this is only for one sample. This is for one sample. And we add them up. So that would be, the total would be summation of for all the sample. This is only for one sample. So the total derivative is for summation of every sample that you have. So now we get the whole equation of derivative. And what we're going to do that, we're going to keep plugging it in here. And this is what we're going to keep opting theta until it get the optimal value in theta. And this is what basically the equation give you. So this is when we're starting from the first point, which give you the equation. Where was that equation? Okay, so that's the equation that we get, and this would be your function for each case, give you the probability. So that's how actually theta is calculated. So this is kind of math behind this segment function that can use that for logistic regression for classification of a binary classification. Now, so let's look into that example in Python. So this example is it's coming from breast cancer data sets, and the library is scikit-learn, which actually we can, this is the main resource basically for using any machine learning algorithm. See that we import that. We have few things. This is our data set, breast cancer. You can look into that. It has a lot of information. This part is actually the features. We have the target 0 or 1. So if this the person has cancer or not. Get some sort of descriptions and features and names so you can look into that. Description of data sets, give the name of the features or attribute, which you can look into that. Importing the features and the target. Couple things. So you see that in here, the data set is split. They do that kind of like a 80-20%, 80% you do that for the train part, and 20% for the test part. So basically test part, you don't see that to your model. So you can think of that as examples that you do. You do few example to learn the idea. For instance, for working with Python code, and to get that idea. And 20% you don't actually you do that as a test, which you don't look into. You don't look into the solution. So we wanted to evaluate so if you get an idea, if you understood the topic. So that's the same idea. We scale the data using, there are different ways to scale the data. And the reason to do that is scaling. So any time that you have gradient descent, scale matter, the range of features matter. If you features, so for instance, you think that this is not example house sales price. So this is not what you can use that for classification. This is a regression problem. But house size, you can have like a square feet of the house size. You can have number of bedroom and bathroom. So these sizes are different in different ranges. So for instance, this is 2,000 square feet and number of bedroom is 4. So they're in different ranges. So actually, when you use the gradient descent to calculate this coefficients for this case, and the same idea, we are using gradient descents in here, it actually affects the model. So that's what we scale that. So that's the idea. We look into that, run logistic regression, and we train that. I will see that based on our 80%. We train that, and we actually predict that on the test part to basically look like assignment that you don't have the solution. And same thing, we evaluate our model. We'll see that 90%. Yeah, actually that correctly. And this is actually the model 90% correct. So, and also we can, so those data, when we train the model, they actually generate the data. We can get those data, which is this parameter. So these are all optimized data based on training data set that we did that. So these are all data calculated. Okay, I think that's it. Thank you very much for watching. Until next video.